Okay, so in this video we will cover three optimization problems. So first one is about HighOptic, then we will do one about TelecomOne, and then we will do about TelecomOptic. So here the idea is that there are two companies, HighOptic and TelecomOne, and then at some point they merge together. And then we want to see what happens to their cost and what happens to how much to be delivered from each of the supply locations to each of the demand locations. So here is our scenario. Let's go through the scenario first. So here we have about 6 supply locations, okay, and we have about 6 demand locations, okay. And here each of these cells here, they are cost per 1000 units for production and transportation. For instance, this one here could be, it is the cost for 1000 units of production and transportation cost from Wichita to Omaha. Here we have to remember that all the costs are in thousand and all the demand or capacity, they are in millions. Okay, units are in millions and the costs are in thousands. And here you see we have some fixed costs. So if my supply location Baltimore is open, I have a fixed cost of about 7 million, 7.65 million. If this one is open, then we have about 3.5 million. So we have fixed cost for having each of the supply locations open or closed. And this is our capacity in millions. So the capacity of Baltimore is about 80 million. So this is the capacity, okay, for each of the supply locations. So now here, the first case, HighOptic, they operate only in this part. So they have 2 supply locations and they serve to these 3 demand locations, okay. So now what we have to see is that to meet the demand, so they have like, these are the demands, 6 million, 7 million and 11 million in these 3 locations where they serve, okay. And we have to see that if they should have both the plants open or if they should have only one plants open, and how much to deliver from each of these supply locations to each of these demand locations. That's what we want to find out and optimize. And normally for constraint for the supply side, we will do this calculation of excess capacity. So here what we see is that, so for Baltimore, although in this case we don't need Baltimore, but we form the equations so that we will be able to use them later in other 2 cases. Okay. So here you see for Baltimore, so first I have to find my capacity. So my capacity is I4, so that's my capacity only when it is open. So that is in H14. If it's open, then this is my capacity, minus the sum of this part here. So all the deliveries that I will make from these supply locations, okay, that is my excess capacity formulation, okay. So we can see for let's say for these 2 locations that are important at the moment in this case. So here you see that we have I5 multiplied with H15, and then we deduct this sum of this demand, okay. So that's how it is for all the capacity locations. And we also define the unmet demand, okay. And to define that here, what we do is we simply select the demand at that location. So for instance, for Atlanta, our demand is 10 million. So we select that one that is in cell B9 here, okay. So it's cell B9, okay. So, and we deduct the demand delivered to that location. So sum of these 2. In this case, we are considering 2 of them. Actually, in this case, we are not going to use them at all. We are only going to use from here. Okay, so yeah, exactly from here, but we still formulated the previous ones as well. So here you see we meet 6. We have demand of 6 unit, and we deduct the sum of this demand that we deliver from our supply locations. Okay, so that's how we define our unmet demand. And normally in these excess capacity and unmet demand, we will use them in our constraints, okay. And if we look into our objective function, that is to minimize the cost. So first we have E15 to G16, this part, okay, the unit we supply multiplied with this part, the cost for delivering the units, okay. So that's what we see here. And we do the sum product so that each of them get multiplied and then added up. And then we also have some fixed cost. So this part is the variable cost, but we also have some fixed cost which comes here. So if my plant is open, then I will have some fixed cost, and that comes into this part of the equation, okay. So if the plants are closed, we'll have 0, 0, then we will have no cost. Okay. So now let's look into our solver, into the optimization problem. So I go to data and I go to solver. So here you see I have the thing set up B32. So here it is, B32. So this is what we will minimize, and we say minimize by changing variables here. These parts only, these are my decision variables. Okay, so we will change only this part of the decision variables. And then let's have a look into our constraints. So the first constraint is B23 and 24 should be greater than or equal to 0. Okay, so we have B23 and B24, these are our excess capacity. Okay, they should be greater than or equal to 0. So it means that we can either use all of our capacity or we can have excess capacity, but we cannot have negative capacity, right? So now let's look into this one, E15 to H16. So here it is, E15 to H16, all this part. Okay, E15 to H16. All this part should be greater than or equal to 0. So we are basically saying that these values should be positive numbers. That's it, nothing much. Then here E29 to G29. So here we are saying that these unmet demand, they should be 0. So we have to meet all the demand. And then for binary, here these plant locations, if they're open or not. So if it's open, then 1. If it's closed, then we'll have the value of 0. Okay, so that's why we call them, these two are binary. And then we can simply solve it. Here I see that we are using GRG nonlinear, but we can try also the simplex one, and let's see if it works. You know, something I have realized is that the solutions in the book and the solutions we get, they differ a little bit time to time. And I think it could be based on the solver we are using. Some of the solvers maybe are not so advanced, or like they had some limitations, but the recent ones may be capable of solving them. So I don't know the exact reason, but I see that there are some deviation time to time. But let's try to solve it. And we actually found a solution. And this is our solution, the total cost. Okay, and we should have only one of them open. And this is our the demand. So we should have only this location open and serve to Denver 6 million from here to Denver, 7 million to Omaha, and 7 million to Omaha, and 11 million to Portland. So that's how we should actually design our supply chain in this case. We see that all our demand are met. We see that we don't have any excess capacity, so use all the capacity, and this is our cost. Okay. So now let's move to the next case, the Telecom one, which has the same formulation, exact same formulation, but in this case, they have only these three. Baltimore and Memphis and Wichita. They have only these three locations, supply locations, and they have these three demand locations. So we'll actually hover around this highlighted part only. Okay. All the equations are exactly the same as the previous case, as you can see, right? All of them are exactly the same. See, yeah. And for our cost optimization, you see that we have some product of, first this part multiplied with this part, plus then this part multiplied with this part, okay? Yeah. And then we have the fixed cost. So fixed cost, we have these two, this one and this one, plus the fixed cost of these two multiplied with this part, okay? So that's our total objective function, okay? You can see it here. Oops. So now we are going to minimize it, and again I'm going to go to solver, and we see that we have a setup here, so we minimize this, okay? And by changing values here, you can see we have different ranges here. So B14 to D14, we use B14 to D14, then we say comma, then we say H14, then we can say, yeah, by that we mean that, okay, we will change this one because we are not dragging all of them, because we will not change these parts, okay? We will only be dealing with the Baltimore, Memphis, and Wichita. That's why we are using comma to define them separately, okay? Then we have B17 to D18, okay, this part. And then again we have H17 to H18, so these two here. Okay, so these are the values that we will be able to change. And if you look into our constraints here, so the first one, B22 to B27, all of them should be 0. Okay, B22 to B27. So we are saying all of them should be 0. So actually we don't need all of them. We need only the 3 that are concerned here, that we focus on here. But it's okay to put all of them because they will not be considered. The rest which are not used will not be considered because they are not considered in the decision variable here in the cells here. So it's okay. And B29 to D29. So this part to this part, this should be 0. Our unmet demand should be 0. And we say that H14 should be binary, this one, and also H17 and 18. These two should be binary. And then we click solve. And we get a solution. And our solution is about 226636. Okay. So these are the cost we get in these two cases. In the first case, it was about 20765. And here, this is the cost. So just quickly, if I want to see how much it is, 20765. Okay, and you cannot see it because I think I have the white color there. So if we look into the sum of them, it is about 47401. Okay, and actually if you look in the book, you will see that they have a different solution for this part. They have a bit higher one when they use the non-linear function, which I do not agree with. We could get to a lower cost, which we get here. So why would I go for a higher one? They have like 21,000 something. Right. Anyway, so now let's move to the TelecomOptic. So here the idea is that if these two companies merge and then they supply from all these locations to all the demand, then what will happen to our total cost? And actually in the book they show that actually you can minimize the cost, but now in this solution I see that we actually have the same cost. But anyway, still the dynamics of how much to supply from each of the supply side to each of the demand location could change a little bit. So now let's solve it. So we have the same problem formulation here. Okay, everything is same as before. If you look into the excess capacity, we'll see that now we consider all the cells here. Okay, and also all the cells for each of them. So now we consider like optimization problem of the whole scenario here. Okay. And for unmet demand, again, you see we considered all of them. So B9 is our total demand and deduct sum of all these demand served, okay, from all the locations. So for each case, we have the same, okay. And for cost objective function, you will see that we multiply. So we take the sum product of all the demand served from all the supply locations, multiply with their unit cost, and we sum them up. And also the second part for the fixed cost, you see that if the plants are open and their fixed costs are also multiplied and then taken sum of. Okay, so that's how it is. And now let's go to solver and we will just see how our solution looks like. So again, we have the same formulation. We minimize this one. Okay, we minimize this by changing cells. Now you see that we actually change all of it. So we started B14. Okay, we started B14, you can see, and then we ended H18. So we can now change all of them. Okay, that's what we are changing now. And here you will see also in the constraint we can change all of them. So B14 to H18, all of them should be positive values. B22 to B26. So our B22 to B26, all of them should be. Can I go down a bit? No. So our B22 to B26 here, you see all of them, all the excess capacity should be 0 or higher. So we can have excess capacity or all capacity are used, but we cannot have negative capacity. And then B29 to G29, all the demand, they should be 0, they should be met. And here, this line here, H14 to H18, they are binary, they can be only 0 or 1. And then we use the simplex and we go for solve, and we have found an integer solution with tolerance. Okay, so here you see that this is our solution. So we see that actually the cost here is more or less the same as what we were having before. But did anything change here? We will have 3 different locations. Yes, we will have Baltimore and this one, Chenene, and then we have Memphis. We will have these 3 locations open, which is a bit different than what we had before. So before we had we were considering this Chenene, and from here we were considering Baltimore and Memphis. Actually, we have the same solution. Yeah, when we consider all of them, we have the same solution. And the number of demand, did it change? Let's have a look quickly. I don't think it changed much. We had 82, then 000, and here we have 82000. So it didn't really change much. It is more or less the same, and that's why we get the same cost. Okay, so that's how we can solve a mixed integer linear programming model. Here in this program we have the components of integer programming and also the linear optimization. So we combine both of them.